Hello everyone, my name is Qian. Thank you so much for your time watching this video. I'm presenting the project result for our Austin team. This presentation is for the second milestone for fellowship.ai. As you can see, there are 3 team members. They are Caesar, Yash, and me, Qian. The project name for this team is Detection of the Damaged Flooring. Let us have a look of the content. First, I'm going to introduce the project information. Then it's about the data collection, following by the data cleaning, and then it's EDA, modeling, result, and the further discussion. The goal of this project is to detect the damaged floor in house or office. The application is quite obviously for, say, like for the client, if they want to buy a house or sell a house, then this app or this application can show the clients the issues of the floor. We are going to stick with the binary classifier. Let us have a look about the damaged and the normal floor. You can see this one is a damaged floor because there is a crack, and this is the normal floor, and the damaged floor and the normal floor. For this project, there are several challenges. The first one is there are too many types of floors. Like we have the wooden one, and this is the stone, and this is tiles, and maybe this is tiles, I don't know, but the carpet, and the wooden, and even we have this kind of art floor. You know, you can see there is a big flower or pattern on the floor, and like this one. Personally, I don't like to live in such room, but obviously this kind of floor existing in the world. This is the challenging one for the project. Then for the challenging two is it's hard to say what kind of floor is damaged and what kind of floor is normal. Let us say this one. Maybe we can say that this floor is damaged because we can see there are some lines bumped up. And if we tell the machine this image, the first image is damaged, then how about the second image? There are some tiny lines as well, but I would say that the second image is normal floor, so that will confuse the machine. And they say for this one, obviously this floor is damaged, and this floor is damaged. Somehow the machine will learn, okay, there are some kind of pattern on the floor, means the floor is damaged. Then if the machine learn this knowledge, get this knowledge, then how about this one? This one, we can see that there are some pattern on the floor. This pattern is not the regular pattern. But as a human, we know that this is a normal floor. But then it's a little bit hard for a machine to tell the difference between this kind of floor or this kind of floor with this kind of damaged floor. So this is the challenge too. Okay, let us talk about the data collection. We use the Google image to collect the data. And when we collect the data, as what I said, there are many types of flooring. So when we collect the data, we for current project, we only focused on the wooden floor, and a laminated, and a ceramic, and a bathroom tiles floor. Say like this one is the wooden, this one is laminate, this one is ceramic, and this one is bathroom tiles. When we collect all these images, then we allocate them into two folders, one named normal, another one named damaged. After the data collection, then we do the data cleaning. First, we manually delete some duplicated data images, and then we use the image cleaner function to clean some misclassified images. As we can see, there are less damaged flooring images and more normal flooring images. And for the damaged flooring, normally the images are zoom in image. And for the normal image, then normally it's not only the floor in the picture. Normally they including the other items in the picture, on the picture as well. For example, the furnitures. And we collect 776 damaged floor and another about 700 normal images. And this is the data allocation about the training set and the valid data set. Let us have a look about the image size. For the normal image, majority of them is between 500 to 1,500, and is similar for the damaged image as well. Just some a little bit of the minor images that is oversized. And let us have a look of the normal floor. We can see that there are so many type of floor. If we look at the pattern of the floor, then this one is a wooden one. This one is a tile, but it's kind of grid pattern on a tile. And this is a red square on a tile as well. And then let us have a look about the damaged floor. There are so many types of damaged. Say like this one is wooden one, normally get old, and they have a crack on the tile, this one, and this one bumps up for the wooden floor, and these are just too dirty. And now for this project, we used two models to to do the modeling. One is the RES Net 34, another one is mix up. For the RES Net 34, we did it with the image size from 64 to 224, and together with the image cleaner or no image cleaner. Say for this table, then this means the content of this table is about the accuracy, and using the model RES Net 34, and all experiments was done in 4 cycles. And this one is the without applying the image cleaner to the data set. Then the data set is 200, the size is 224, and they did it with frozen and unfrozen training. Then for this one, it's the same. I applied the image cleaner to the data set and then transform the data set between different size and did it in the frozen and unfrozen as well. Let us have a result. Have a look about the result. So we can see this one, we didn't apply the image cleaner on the data set, and the size is 224. For the frozen model, we got 85% accuracy, and for the unfrozen is 89%. If we apply the image cleaner to the data set and then resize the data set to size 64, for frozen model we got 82% accuracy, and for unfrozen we got 83% accuracy. It's a little bit slightly better. And then for the size 128, we can see that the frozen model have a very low accuracy, but when we unfrozen the model, we got a 84% accuracy. Similarly, for the 224, 52% accuracy for frozen, and about 90% accuracy for the unfrozen. What can we learn from this experiment? First, for the unfrozen model, apply the image cleaner or not does not improve much. We can see if we see this column, we can see that this one, the green one, is without image cleaner, and these results in red are with image cleaner, but they all roughly about 90%. There are not much difference or improve. And the second result we can get is the larger size, the higher accuracy. Say for if we look at these three rows, we can see that when size 64, we got 83% accuracy. When the size is 128, that is 84. When the size becomes 224, then the accuracy increased to 90. So the larger size, the higher accuracy. And generally speaking, the unfrozen model is better than the frozen model. If we compare this column together with this column, we can easily get that result, conclusion. One other thing I want to point out is the accuracy of size 64 for the frozen one. There is 82. You know, it's much higher than the other two models. This result is a little bit odd for me. Now let us have a look at the mix-up model. Then I did the mix-up model to without the image cleaner, and done it under the frozen and unfrozen model. And the same is for 4 cycles for every single experiment. Let us have a look at the result. We can see that, like here, the frozen one, they are the same size. The frozen one is 85%, and frozen is 89%. And then when we go to the mix-up model, the frozen one become 64%, and frozen is 79%. So that means for this case, the mix-up model does not improve the accuracy. Let us have a look about the result of the confusion matrix. For the model IES net 34, apply on the image size is 224. together with the image cleaner. We can see that there are 12 images, and together another 21 images are misclassified. And then this is the top loss prediction. We can see, for example, this first image that is normal, but it predicts as normal, but actually it is a damaged one. For me as a human, it even feel a little bit hard to tell it is normal or damaged. Really depends on the standard. If you have a very high standard, want the really perfect flow, then this one damage definitely is not perfect. But I would say that this flow is a little bit, maybe some mold on it, not that clean. Maybe that's the reason we classified it as a damaged image. And they say, when let us have a look the last image. The model predicted it as a normal one, but actually it is a damaged one. I would say that we know that there are some dirty stains. But as what I say, it's for machine, it's very hard to tell this is the stain or it's just a pattern of the carpet. So I would not blame the training result that much for this image. Let us have a look of the heat map. Not much special. Okay, let us have a look another the top losses. These ones say that they best predict this normal, this is damaged, then predict as a damaged, and have a look about with the heat map. Okay, we can see that the machine or the model think the furniture is more important. Now here is furniture. This is the window. Furniture. This is a TV, and here is around the whole of the on the floor, and this is the stand on the floor. And this is the confusion matrix for the experiment results apply on the data set without the image cleaner. And the model is IES net 34. We can see that similar to the previous confusion matrix, we can see there are 19 and 21 misclassified samples. This is the top loss. Top loss. Okay, let us have a look at the last image. The model predicted as a normal one, but actually we classified it as a damaged one. Just as what I say, the reason this floor is damaged is because obviously it's because the bumped up lines. But as we can see, we have this kind of wooden flooring as well, and there are some lines as well. So that is a little bit hard for the machine to tell under what situation is normal and under what situation it is damaged. This is the result together with the heat map. And we can see from here, it focus on this on the hole on the floor. This is another the best predict. And it tell us that, say, like this is this hole on the floor, and this is the furniture, then furniture. This is the wall or the door and the window. That actually they tell us a lot. That means the furniture on the images affects the result quite a lot. Okay, I would like to do some further discussion for this project. Firstly, is one of the thing that is the size 64 has a high accuracy among with other size. Say if we look at this column, we can see that for the frozen model and the same data set, the 64 has a 82% accuracy, and the other two data set have about 50. For me, I think this one is a little bit odd. It's a little hard to explain why. The second point I want to discuss is about the training result values. We can see that we got a 92% accuracy last night when I did this experiment. For the identical data sets and identical parameters, and then today when I did it again, and the best accuracy become only 88. So even I set the random number seed, but the result still varies. Give me the feeling that each time when you do the experiment, the performance is not that stable. And the third point I would like to discuss is about the training time. If we see this one, we can see that the training time is about 10 minutes for per cycle. And if we do it for 4 cycles, that means it's 40 minutes for training one model. And if we do it for the frozen and unfrozen, that is 40 minutes times 2, that is 80 minutes. And if we do it for different sizes, then times another 3. That is a lot of time for training. I think maybe fast AI should be faster a little bit. Maybe this is the things we can improve in the future for the fast AI library. Okay, basically that's it for the project. Thank you so much for your time for watching this video. Thanks, bye.